Hello and welcome to the online schooling part 1, Introduction to Member Design, RFEM 6 for students. My name is Richard Hase, and I will go with the first part of the schooling with you and will introduce you to RFEM 6. And the second part of the online schooling will make my colleague Jonas. But first, to my person, I work for Dlubal in the product engineering for concrete and also in the customer support. And my colleague will introduce himself.
All right. Good afternoon to everyone. We are struggling a bit because the overlay of the go-to webinar has changed, unfortunately, today. So we are not very familiar with it. But we hope we can manage it and make the best out of it. So my name is Jonas Bien, and I'm presenting the second half of this training. I'm also working in the support and product engineering department of Dlubal Software. And my responsibilities are steel design and structural stability. During this webinar, or the first half of the webinar, I will try to answer your questions that you can ask via chat.
Okay, then we can turn off our cameras. And Jonas, can you turn off your camera in the bottom line?
Yes.
Yeah, okay, perfect. Okay. Yeah, I don't know if you have the layout of the program like we have, then it looks a little bit in another way. But when you find a button with the chat and with the question menu, then you can ask during the online training, and my colleague and me later will answer on these questions. And if you have following questions, you can write an email to info@dlubal.com, and yeah, we will help you then. Okay, yeah, this is the first part of the online training. Today we show the beginning of RFEM 6. We will design some members and we'll show you the graphical user face. And yeah, in the following days, weeks, there will come other events like our section. This is another program where you can design cross sections and create own sections. And there is also a connection between RFEM 6 and our section. So when you design your own sections, you can import or export them to RFEM 6. It's a very good feature. Yeah, then will come an RFEM 6 online training to the FEM. So there will show you how you calculate plates and walls and such things. Today only member. Yeah, and then came the calculation add-ons for timber, concrete, and steel. All events are for free too. And yeah, if you want, you can register there, and they're very informative. And okay, one moment, I must switch. Okay. Before we start, I have a poll for you. I want to know if you can work with RFEM 6 during the presentation, and if not, then I can maybe update my but when you working with RFEM 6 parallel to the webinar, yeah, then I will make it a little bit slower. Moment, then I hope it functions. Effect. Okay, I don't find the right poll. Okay, then let's skip this. And I'm sorry, but yeah, the layout of our GoToWebinar updated today. On Monday, we have another layout, and so I'm sorry for that. So then maybe today without polls. Okay, then I will give you the content of the online training today. I will begin with an introduction to the RFEM user interface. Then we will come to a little introductory example for a single span beam. So the simple of the simple, but yeah, that you see how you can modeling. Then I will give you, I think it was two more examples where you can see modeling different options which you have in RFEM 6. Then we will make a break after 1.5 hours. So circa, and after this break, Jonas will continue with, I think, also two other examples. And then he will continue and show you the influence of the second order theory. And at the end, stability analysis. And yeah, okay. Then, moment again. Okay, yeah, then that's the user interface of RFEM 6. I will only show you fast, and then I will switch to the program. It's you can see it in progress. I think it's more practicable. Yeah. So first we have here the navigator, and the navigator is split in different parts. The data, the display, the view, and after calculation, the result navigator. And in the navigator data, you can create all model objects, can model the load cases and also calculation options. Yeah, the menu bar. There also you can have the same options like in the navigator, and also like import and export some other datas or print and such more. Then we have two shortcut toolbars on the top side and on the bottom side, and you can manual or customize this toolbars. Every command you find here, you can put it in these lines, but I will show you later on a little example. Yeah, it's for a fast workflow. Then we have here the search function. If you don't know, okay, where I can find some commands, you can put here some keywords and it give a direct link to this command. Then we have here the view cube to switch the perspective. And they link to the global axis system, but I will show you also in during modeling. Okay, then we have here the workspace. The workspace is the whole area where you can modeling for example, nodes, lines, and the members later and surfaces all all objects are visible here in the middle in the workspace. And then we have relative new, an AI assistant. She's called Mia, and Mia, you can ask everything and about the program, but also general statistical questions. And yeah, I will show you that later in the first modeling example, and we can prove how fit she is in the statistical knowledge. Okay, and at the end we have the table option, and in the table option you can also create and selecting model types and loads, and so you can say in the navigator, in the menu bar, toolbar, or in the table, everywhere you find the symbols and buttons for modeling, for the load cases, and so you have different types of modeling ways. So how it fit for the best way for you, you can choose it. Okay. Yeah, then let's come to our first example. A single span beam with a length of 7 meter 50 and at 450 nodal load with 10 kilonewton. And yeah, first I will show you the modeling, then how I create such loads, then we will calculate this, and yeah, with Mia we make a control. And okay, so maybe then let's switch to RFEM. Yeah, okay, back to the user interface. So for example, when we want to create nodes, nodes are the beginning of every modeling. And yeah, nodes are the begin, and on these nodes you can put lines or members, and surfaces are or needs these lines at border. So yeah, for example, with nodes, so you can start here in the navigator data, can click for a new node, and I will show you. You can also here in the menu, basic, can also here nodes, or in the table you have also option with the coordinates to create nodes, or even here in the shortcut. So you see you have different ways to modeling, but yeah, okay, then let's start. I will close this, and then let's start with a new model. I call it online training. And yeah, before we start, a little information. The add-ons you see here in the next tab, like the design add-ons for concrete, steel, timber, you must activate it here in the base data. And when you activate it, some add-ons here, you will see in the navigator data, and everywhere then the possibilities are increased. And then for example, you can design concrete objects. If you don't activate this add-ons, it's pure static program. So yeah, whatever you need, you must activate this add-ons. And okay. Yeah, to the base data. Okay. Then the type of model is very important. The default setting is 3D, and 3D you have 6 degrees of freedom. So you must thinking about more deep what is important, what I must control, and we only have simple examples here, so we can switch to 2D. You see here the degrees, and so it's simple enough for this kind of models. So then we say OK. And first of all, you see here this black background, and I will switch. You can stay it in black, but I will switch to a white background that you can see it better. Then you go here again to display properties and switch here between white and dark background. And I choose now for the presentation to the white background, say OK. OK. Yeah, maybe to the view cube before we start modeling. So you can left click on this cube and you see you can switch the views. How I say it's connected to the global axis system. So you see the Y direction when I click on the Y, or when I go so to the X. So okay, and the same idea is here with views in X, Y, Z, or you can choose here other directions. And another option is when you press Control and the middle mouse button, you can also turn around here. Okay, but let's start with the modeling. Yeah, our system, I said we have 7.50 meter long single span. So then let's beginning with the nodes. Then I choose here the shortcut and I click to the 0, 0 coordinate with its left. And now we have the first little problem. So when I go here, we see the 4 meter, and when I go here, 5 meter. So we want to in the middle. Now we have different options. First, I can click on this node and can, in this case, it fits perfect because we start in 0, 0 coordinate. Then I could change the X coordinate to 450 and say OK. And now you see, OK, it's on the 450 how we want it. But you have also another option. You can go here to this button, settings on work plane. And the default setting is here, the space 1 meter. You can see here the picture. And we want to change it to 1/2 meter. Say OK. When I delete my node again, then we can see, okay, here 350 for 450. And so you have these two options to create nodes on easy way. Okay, then we need the last point at coordinate 750. Let's do it in this way. Okay. And yeah, maybe I set it to the default setting. You can also here. Okay. So now we have 3 nodes. Oh, maybe I showed this before. So when you left click and go from left to right, you see in color, and from right to left, you see this blue. So maybe I will continue first with a line. Wait, let's go to the node, to the this, and again to this. So, and yeah, when I from left to right with this orange color, and for example here over this line on this node, you see, okay, only this node get selected. But when I from right to left, you see, okay, the line and the node is selected. So you have these both options. The orange color, there's only selected the object which is complete in this rectangular, and in the blue you need only a little of this object and selected. Okay, so now we have 3 nodes and 2 lines, and so we can select these both lines, go with right click lines and edit, and now this logic is defined in whole RFEM6. Maybe you remember with the base data with the add-ons where I say, okay, you must activate it, that the actions are to use. So it is the same principle here. So we have this line and one transform this line or give this line some properties, and we say, okay, we want transform this line to members. Then open a new menu, the new member menu. And what can we see here? A member type. So the beam is, I say, the default type. The beam give all forces to other objects. So, for example, when we go to the tension, you can all time orient in these pictures. So we see here, okay, all forces at beam, and tension, you see only tension forces can transfer to other objects. So same for compression, it's here only negative forces. But let's go to another member type. Here is a definable stiffness. Maybe it's interesting for you in your study time. There you see we have a new tab here, definable stiffness, and want here create a new stiffness type. And here you can see you can define manual all stiffnesses, torsional stiffness, bending stiffness, and so on. And maybe it's perfect for your book exercise, and you can manual create your beam in this way. So okay, but let's start with the most typical beam, or remember the beam type. And for this beam, we need a section you see here in the next tab. And now you have this button. It goes to the library. We will click on it. And now you see all section types you can choose. Here also what I said before, we start from a section. So when you create a section, cross sections, which are not tabled here. You can import from our section here. But let's take a standardized section. Let's say we want to maybe here, such one, 180. And now you see this yellow color because we don't have create material. And so let's create one. There's again a library button. And okay, let's say European Union, material step steel. And then you see, oh my God, so much steel. How can I find my steel I'm searching for? And you see here this searching function. And let's say take an S235 and the shown steels options are reduced. And here you can see, okay, let's such steel, say okay, and you see the yellow switch to the blue. The blue stands in our program for steel, and we say okay. Now we have an 180 HEA with the steel as 235. Say okay and okay. And now we can see our property-less lines are transformed to such members. Okay, so what we need are the supports we have here and the loads. But before I modeling this, I will give our AI assistants the chance, and she will calculate, and then we can control the RFEM6 results to the results of our AI assistant. I copy from my document. Okay, I say here a single beam with length of 7.50 meters with a single load on 450 with 10 kilonewton, and I want to know the bending moment at a length of 450. And yeah, then we start, and Mia show us how good she is with her statistical knowledge. So, and parallel we can modeling the nodal supports. There, okay, when we go to this button, you see the degrees of freedom, the translational and the rotational. And yeah, we say, okay, an X direction and Z direction fixed. We want that on the left side. Say, okay. And you see maybe when you click with the right mouse and this button, you can increase the size. And okay, we need another. We say we need here a nodal support with roller properties, and we say this. Take our point. Okay. And yeah, what is missing? Maybe to control the length again, you can click here for dimensions. Okay, didn't I click on my first node? Oh, was wrong, sorry. Let's linear on this node, and this node. Yeah, then we must see the plane, and we must choose here the second plane. Okay, that's fine. And we see, okay, our length 453 meter. We have our control, our 7 meter 50 long single span. And yeah, now we need our nodal load. Then we go, or we have here the option loads, nodal loads. But yeah, you already can do it here in the shortcut, new nodal load, or even loads, nodal loads. So you have everywhere, also in the table, you have the chance or the option to modeling in different ways. So let's do it this way. A new nodal load on our load case self-weight and take this 10 kilonewton, Z direction or fit. Okay, on this node, say okay. And now we will check what Mia is calculated. She say, okay, at this point with formulas, and you can control it, we should get 18 kilonewton meter as bending moment at this point. Then, okay, let's check it. On this button, you can start calculation. For this load case, you have also the option here on the calculate all, or when you have more than one load case or a lot of load combinations and other things, you can see here, you can select what the program should calculate. But okay, global deformations. You see here the navigator results is new because we have calculated and have some results here. But we want to go to the members, internal force, and to the bending moment My. And okay, Mia say we get 18 kilonewton meter, and our program said 20.4. So who's right? I say Mia is right, but what's the reason for this difference? Maybe let's check the support reactions. So we have 10 kilonewton from the top side, and see here 5.3, 7.3. Okay, it's higher than 10. So a thing must be wrong, or not wrong, but how can I say? We must prove some, and the reason is why the load case self-weight. When we go to edit, here we have an active self-weight in that direction. So we have created our steel section, and this steel section give his own self-weight on the structure. And the default setting is that it's deactivated, but I show you how you can activate it. We go to the navigator and here to the display. Then we have here the loads and the self-weight. Okay, and you see here the 0.356 is self-weight of this HEA 180 profile. And that's the reason why the results are not as expected. So let's deactivate here the active self-weight and calculate our self-weight load case again with our no load. And yeah, now you see here our 18 kilonewton meter, exactly that what Mia say. So yeah, maybe Mia can assist you and with statistical questions, or even if you have questions about the program, you can write it here and Mia will give you answers. And yeah, good. Then we have this. Yeah, so the internal forces. Yeah, one side we see here the My, but we also can see here the shear forces. Let's see, 10, 4, and also the deformations. And yeah, that's the options, stress strains, and yeah, you have a lot of options of the results to see them. Okay, that's enough for my first example. Then let's go to the next, a two-span beam with altering load positions. So we will create more than one load case. We will do 3. And yeah, then I will show you the combination wizard from RFEM 6, when you have different action types like self-weight and snow, wind, and so on, and how we combine it with the gamma and C factors. Yeah. Okay, and another things, but let's start with the modeling of our second example. Okay, Mia, thanks. Then I will delete my model. And yeah, we have 10 meter of the whole length. So you have the options with the nodes and with the lines I showed you before, but there is also a faster option. You can create here a new single member. We switch to another profile. So I create here a new section for our member. And yeah, you have the options with the library, but you also can write it here, the name of the section, and RFEM will find the section 2. Okay, we have a HEB 300, and now you see the fitting standard. Let's take this with the Euro norm, and we say OK, say OK, and from 0, and we want to go to 10 meters. You see, it's a faster way than selecting the nodes and then the lines and transform the lines. So what I want to show you the principle of RFEM 6, because behind this member is all time the nodes and the lines, but that's the most more faster way. Good. Now we have a single span, but we want a two-span beam. So we click with the right mouse on this member, divide member, and the distance. And now you have the option between percent and meter. And yeah, 50%, 5 meter, that's exactly that what we want. So we divide our member and have now 2 5 meter beams. And now we need again our nodal supports. Again, this type for our left node, say OK, and again such roller type nodal supports for the other two nodes and say OK. And OK, then we have this. And now I will show you how you create new load case. You can right click here, new load case, or even in the shortcut, new load case, and again in the menu or in the table, so you are free. But I will show you here the shortcut. There is our self weight. We want to activate the self weight again. And here you see the action category. The default setting is that this combination wizard is activated. So you have this action categories, and with help of this actions, he can, or he know how to combine these actions in the load combinations. But I will show you. Let's take for our load case number 2, impose loads, category A, and say here left, and copy the right, so left and right field. Okay, now you can see the actions, our permanent with load case 1, and here our imposed loads category A with load case 2 and 3. And yeah, this for design situations are the default. Let's have a look at our ULS. So here you see Eurocode and information, the combination rules with this gamma and psi factors. Now we see he combines the actions, the A1 and A2 of our self weight and the other action, and here the load combinations. Okay, maybe here it's not so interesting, but I have another example where we have more than these two load cases. But you can see here he combine after this rule all load combinations. Okay, that's okay. And now for our load case 1, we want to create a new member load, right click, and have 2.5 on both members. And you see, okay, he created. And for the left, the same new member load. On the left field, we want to 5 kilonewton meter, say on the left field. And now I could press the OK button, then close the load option here. But I want continue with my right field. So when I click here, apply and next, then I can see, okay, he created, and I can easily switch to another load case. And okay, the same with 5 on the right field, and say okay. And now we are ready with our loads, and I close this with okay. Okay, and we can control it. We have the self weight plus the self weight of the HEB section, but I have deactivated, but you can activate it again. then our left field load, and on the right. Yeah, maybe when you make controls with examples from literature, then it could be possible that you get other results than in RFEM 6. And the reason I show you, it's you can see it in the sections. And you see here this option, deactivate shear stiffness. So the default setting is that RFEM 6 calculate with the axial and the shear stiffnesses, but in literature examples, most time the shear stiffness they don't calculate with this kind of stiffnesses. So you can click it here. So you deactivate it and make the shear stiffness to infinity. Yeah, so I show you the difference maybe with the shear stiffness. And yeah, let's show you on the self weight. So you have here the show results. But let's show you another way to calculate, and we want to calculate the self weight. Say okay. Okay, so when we see the deformations, we have 0.3 millimeter here. And when I deactivate the shear stiffness, so make the shear stiffness to infinity, let's see, we have 0.3. Say okay. We get only 0.2. So the system get more stiffness because the shear stiffness is not or the shear stiffness is with an infinity size. So that you must know if you calculate it with literature examples. Okay, then deactivate it here, but I let it for our example active. Okay, good. Then let's calculate all, and then I show you the results and explain something. Okay, maybe we can choose it here to the wireframe model. It's then better visible. Let's see the bending moments, my. We can also deactivate our self weights, our showing loads. Okay, and we switch to our design situation. And now we see, okay, we have here max and min values. And why we get it here in this design situation. The reason is I show you how he create after this combination rules. And yeah, here for the ULS, you see, okay, he have 4 combinations in this case. And out of this 4, on every location, he show you the min and the max values. So Okay, so, and now we want to know, okay, where this this result come from. So this minus 37, which combination give us this result, and therefore you go here to static analysis, results by member, go to internal forces, and now we're member one. That's right, on the end of member one. And here the extremes, and this blue and this red symbols show you the max minimum values. So, and now we find our minus 37, and here is a corresponding loading. So, and you say the combination number 3 give us this maximum or minimum value of the bending moment. So then let's prove it. Combination number 3. Let's show the loads again. And you see, okay, we have factorized our self-weight. And here on the left and the right field loads. So it makes sense that this one gives us this minus 37 bending moment. Okay, then let's check it for a field bending moment. So this 26.78, and you say, okay, it's come from combination number 2. And combination number 2, you see here our self-weight with load case number 2. And load case number 2 was the load on the left field. So, okay. The same you can do for the support reactions. So maybe the member results deactivate, and let's see as our support reactions. Now we want to know, okay, where this 77 kilonewton comes from. Same principle. So results by member, you must switch to results by node, because on this node is the support results by node, and switch here to support forces. And now, okay, see here, that's number 1, and we want to go to number 3. And you can see here number 3, and here we have the 77 also comes from combination number 3, and combination number 3 was, you see it here, self-weight, left and right field load cases. So that fits also well. Okay. Yeah, that was the second example. Then let's switch to the PowerPoint presentation. And yeah, the next example is a Gerber beam or hinged beam. And this system, you see, it's maybe the same from out looking this 2-span beam, only here is a hinge, and through the hinge this 2-span beam gets statically determined. So they're a coupled system of a single span to a single span with a cantilever. And yeah, how we we want to create such a Gerber beam. And in Germany, we have a book with a lot of tables and formulas. And we see here a Gerber beam with 2 times the same length and a formula for the location of the hinge. And our task is now we want to parameterize the structure. So when we have this 5 meter, for example, and say, okay, for the next example, we want 3 meter, that the hinge, we don't must change it manual through this parameter, so that it's actual or that it's automatically actualized. Okay, good. Then let's switch back. Let's say we take the same 2-span beam because it's more easy. Then let's say we want to divide this member and say only, okay, we say 1 meter. And here on this case, we want to have our hinge later. So, but let's first set a dimension. Again, the second plane. Okay, for control. And yeah, you see, oh, say here, okay, maybe through the new GoToWebinar that say the program goodbye. Let's start again, RFEM 6, one moment. Yeah, and another point for this Gerber beam is you see the maximum field bending moment is exact the moment over the support. And yeah, it's for the design check more easy when you have one size for the choose of the section. Okay. Oh, sorry, I open the German one. I switch back to English, sorry. One little moment, please. Okay, now it's open. I think you don't save it. Okay, then let's close and make new. It's fast, so let's say Gerber 2D. And Y. And we want again our beam. Oh, it's okay. So we say our 10 meter. Divide this member with distance 50 and divide again with 1 meter. And our nodal supports. And say here our roller. This one. Okay, a little bigger. Okay. So first, wait. Okay, I will customize. Oh, wrong. Restore and set toolbars to default. Okay, so now I show you how you parameterize your model. So the command is here under edit global parameters. So it's a little bit hidden. So when you can remember, I tell you at the beginning that we have such search function here, and you can type it global parameters, so you can find it there. Or when you working more often with this command, you can customize your toolbar, and therefore you go to view, customize menus and toolbars, and go here for global parameters. And yeah, every commands you can find here or over this searching function. And I want to say, okay, this global parameters I want to add in my toolbar. Then left click, hold the left click, and I will add it here. And yeah, so we have it fast to find. Okay. Then I see for the field length, I call this field and say 5 meter, our actual standard. And here, let's say Gerber or hinge. You can select it how you want. And here we have a definition type of value. And because of this formula, we can add this formula too. But maybe, oh no. Yeah, we can switch between value and formula. Let's choose formula here. And you see now our formula field here is available. So important is when you choose such formulas, you must use a dot instead of a comma. Otherwise, RFEM6 get problems to understand. So from our table book, it was 1.1716. The field length, but this is only, it would be here, but we want to have our Gerber hinge here, so we must say another field length, and now we see, okay, it's at 5 meter 858. Now say okay, now we have our global parameters, and now we must connect our model with these parameters. So we go to, oh wait, before I forget, our dimensions. Okay, so good. Maybe I save it. It's a good thing all time. Okay, so node 3. And now I say I want to have a global parameter, our field length. Go here and say, okay, and insert. Okay, 5 meter was before 2, but you see here this little yellow symbol, and there the fx sign for the formula, and say okay. And our second node, say here, and say okay, we want to edit the formula, and we say 2 times our field. This what's the name of the global parameter? Say okay, and you see here 10 meters. That's right. Okay. And now our Gerber hinge. Say again global parameter. Want to have our Gerber, and you see our 5 meter 858 again with the yellow symbol. Okay, and you see before it was on 1 meter, and you see it switched the length. Okay, the last thing which is missing is our hinge. So let's go to dismember, and again the same principle. So we want a hinge. Important is here you see in this direction. So this is the start, and this is the end of the member. So we need a hinge at the start point. So we click hinge. We get a new tab here, hinge, and we want a member hinge at the start. And yeah, a rotational hinge is that what we want to have. Say okay, and here we see our hinge. It's it's all time it's the biggest size, but you can decrease or increase the size here again. Okay, so then let's view on the self-weight load case if it function. And global deformation we don't want to see. We want to see members, internal forces, and bending moment my. And we see here the same results yeah, in a field and over the support. And now we want to check if the parametrization function. So when I say okay, I don't want 5, I want 7 meter field length. Okay, it's a little bit big. So, and say okay. So you see 7 meter and 7 meter, and the hinge also spring. So then let's prove it. Yeah, and you see, okay, a little difference, but 150, 150. So we can say it's right. And yeah, so you have now a parameterized uh, Gerber Gerber system. And yes, this parameterization you can use for all models you can imagine. And if you have such systems more often than one time, that's really good and save a lot of time. Okay, then that was this example. And now, yeah, at the time we only use the member type. Now I want to show you a frame with a tension member and show you the effect of such member types. And also the combination. You see here we want to modeling snow, wind, and temperature. And yeah, okay. Then we can delete it here. Oh, wait. Sorry. Okay. Yeah. Then let's create our frame. So we have again our HEB 300. Say okay. And 5 meter in the high and 5 meter and 1, 2, 3. And now, okay, our frame is symmetric. So you have the option, okay, you draw 2 other beams, but I will show you an option. Here it's fast, but when you have a big hall and all is symmetric, so you only need to modeling the one half and the other you can make here. You can mirror the objects, and now I will show you how it functions. So you select your objects and say mirror select objects, and yeah, you want to create a copy and must see the plane. So you want to as mirror plane the YZ. So you must change it here to YZ and change a point. Say here this top point and say okay. And now you see you mirrored your system. And yeah, it's for bigger systems or with a big symmetric with symmetric and big systems. It's save a lot of time, and yeah, it's a very nice function. Okay, then let's add our nodal supports here and here. And for the end, our tension beam. Let's go again here, new single member and node beam. Now we want our tension member only positive forces. Okay, and select him here. Oh, yeah, it's the wrong section type, but let's change fast. We go to the library and want a bar type, a round bar with 30 millimeter. Say okay, okay. It looks better. Good. Yeah. Then I want to show you the first the loads. Let's make a new load case. We have here snow. We want to have. And another wind, and yeah, you must choose a fitting action category, and another one temperature and action category temperature. Okay, so now we go to actions. You see, okay, now we have here on this symbols also that fitting action category. And now it's interesting and save also a lot of time, this automatic load combinations with the combination wizard. And okay, that's only the self weight, but look here, we have self weight snow and wind with a leading action category, and the not leading get the psi factors. So or here, and this is very good. And you have more for fatigue or for seismic. So different rules, and with the help of the wizard, you don't need to make it manual. It's fast, and you're on the safe side and have all combinations, all possible combinations. Okay, then let's say okay. I think it's really the problem of the new GoToWebinar. Sorry for that. That's not the standard faults. I will start RFEM new. Okay, restore. I hope he saved it. Okay, then let's fix modeling it again. Wait. Maybe I have it here. Gerber, maybe. Okay, then I have some right materials. Okay, so we had here our 5 meters. Okay. I started new. Must depend on this new GoToWebinar. Normally it don't crash. Cannot be moved. Okay. Then I will try it again, and he is away again. Okay, one more time.
Otherwise, we can maybe go into the coffee break, and I can try to either model it afterwards, or we leave this example.
Oh, okay, maybe yeah, it's a better idea. Yeah, okay, yeah, maybe my PC get some problems with the new GoToWebinar. Yeah, then let's do it in this way. Yeah, then let's go into the coffee break. Jonas, what do you say? Maybe 10 minutes? Or
Yes, let's make a coffee break until 5:30, and then in 10 minutes we meet again and go further and explore some new realms in RFEM.
okay.
All right.
Yeah. Okay, then yeah, have a good break.
See you guys. All right, everybody. On my clock, 10 minutes are passed. So I would like to continue with the second part of the training. Unfortunately, Richard had some problems with his RFEM version. I hope I don't have similar problems, but in the last session 2 days ago, it worked fine for both of us. So that's really strange. Let's hope it's connected with the new GoToWebinar interface. We will see. I didn't mention, or we didn't mention it until now, but this session will be recorded, and you will get a link to the recording together with your attendance certificate via email. But since we are now skipping one of the examples here, and in case you are interested in seeing how this particular example is solved, you can check out the recording of the previous online training within the students training program, which is already on YouTube, or you can also find it on our website, and just watch the webinar from 6 months ago. And there we also calculated this or tackled this example, and with respect to the user interface or the approach on how you can proceed here, nothing changed since then. Okay, so I want to go ahead with the first example after the coffee break, and that would be a suspended single span beam. Here we want to now mix different types of members. We want to model the single span beam with a span of 60 meter 50 as a beam member, which can transfer all kinds of internal forces, so bending moments, shear forces, axial forces, and couple it with truss members, which are shown here in red in this overview. And these truss members will only transfer axial forces. And this secondary red truss structure acts as a suspension for this single span beam, which has a very high span and would fail otherwise if we wouldn't add additional supports by this secondary support structure. Okay, let's go ahead and go to the program. I opened a blank model. The only objects that I already included in this model is material, an S235 mild steel, and an HEB 300 section. This was already defined by Richard, so you know how that worked, and I won't go through that again. The model is also still based on a 2D type model, so we will not yet go into the three-dimensional realm. Yeah, all right. So first of all, we model the single span beam. So therefore, we create a new member with a member type beam. The section would be HEB 300. Click OK. The length should be 60 meter 50. So I don't have a point to grab here. So it's actually hard to find the correct length. So therefore, I would just use this input dialog to determine or to set the length to exactly 16 meter 50. The important part, if you use that, is that you don't go back into the window or into the graphical user interface. So if I type in something here and then go back to the main window of RFEM, it will directly overwrite my input value. So I need to make sure that when I input this value, I hit enter or apply before I leave this window here with my mouse cursor. All right. Alternatively, one other solution would be to adjust the grid or to manually change the coordinate of the second node. There are multiple ways to define this the beam of this exact length. Then we had two additional nodes on this member where we want to connect the vertical truss members. So I divide this member by two intermediate nodes, and I set the option to create a member on node to because I don't have to divide this member this way. It can be stay one single beam element. Then now, how do I define the secondary truss structure best way? One simple way, so we need to make sure I show the task again. The vertical distance of these two nodes is given as 1 meter 40, and the vertical distance at the member ends would be 2 meter 30. So in order to achieve this position of the truss end nodes, or to create these truss end nodes, I can use my copy function. And I think the best option would be to take the nodes on member, so the intermediate nodes, select them, go to the copy function, and say I want to copy these nodes in Z direction by minus 1.4 meters. And then I need to make sure that I want to create a copy. And because these nodes, originally they were nodes on member, but of course when I copy them away from this object, then they are directly transferred into node of the type standard. And now I could like define my truss members between the two nodes. What I could also do, and I want to show you that alternative option. Here it doesn't make so much sense, but in larger structures, that's a very nice feature that you can leverage to speed up modeling process. So I again select the two intermediate nodes, want to create a copy, and then I say in the additional options, I want to step the links. And that means, or that gives me the option to not only copy the nodes, but to directly create lines between the two nodes. And I can also on these lines directly create members. So when I hit OK now, it would copy the nodes, create lines between the base nodes and the newly created nodes, and create member. And how this member should look like, I have to define. I could either give a template member from my structure, or I define a new template, and that I want to do because this definition of this member should differ from the first beam I defined. So I want now to have a truss member, and the section shouldn't be HEB 300, but it should be an IPE 200 beam. So I create a new section, created via the quick search up here, and create a new section number 2 of the type IPE 200. Okay. One thing to add, Richard already told you that on the right side here you see which degrees of freedom these member types have, and there's a very nice indication on what internal forces are transferred at the end nodes. If you are unsure, I want to add that you can always use our online help manual. And in all of the dialogues you find this little box in the lower left corner, which you can click, and what it will do, it will open our online manual, and it will not only open the correct online manual for the program you are using, but also the correct section of the online manual with respect to from where you are opening it. So I would directly come to the edit sections dialog, and I could quickly browse through the different member types and get additional information. So that's a very nice way to get first help. We also have linked additional webinars or articles that are relevant for the manual. So this is a very nice and quick way to get additional information. All right. So the truss member is like a beam that has moment releases at its ends, and I will use this member type for the secondary support structure. And now I have like finished the definition of the beams that I want to create with this move copy command, and then I click OK. And now you can see with the copy command for these nodes, I have directly now 2 additional members, and I don't need to do anything with this. So that's already quite nice. And then in the second step, I would take the outer nodes at the beam start and beam end and copy it in minus 2.3 meter in that direction. I could also, like if I have the dimensions like here in this PowerPoint presentation where I have 1 meter 40 plus 0.9 meters. Of course, I can calculate this in my head, but if I don't want to, or if it's the numbers are not that even or easy to sum, I can also type the mathematical operation in this input dialog, and it will calculate the correct value for me. What is also nice, I can also enter values with units. So if I type in 2,300 millimeters, it will automatically convert it to the unit that I use for this particular input. So this is very smart. But in this case, I wasn't very smart. In this case, I didn't want to create additional members between the 2 nodes that I copied. So I just delete these by selecting them and clicking delete button. And the remaining truss members that define my secondary support structure up here, I can create those by now linking the 4 nodes. Oh, I misclicked, but no problem. I can just drag and drop my end node of this member and release it on the node I created before. So that's also no big deal. So now I have defined all the members, and I mean I can already see that they have different cross sections when I activate the rendered view. So up here you can toggle between different display modes for members. You can toggle between a transparent rendered mode, the wireframe model, and the solid rendered mode. But sometimes it's hard to see, like, are there really different sections? They could have the same height, but different section dimensions or whatever. And in that context, I want to show you another function that allows you to easily distinguish between different sections or beam types. And therefore, you can go to the Display Navigator tab, which is the second here in our navigator. And under colors of rendered objects, you can color, for example, the beams, the members, by its properties. For example, you can color it by member type. And if I activate that, I see that this lower member now is colored in blue, and blue stands for beam member type. And the rest of the structure is colored in green, which stands for truss member type. And I can also do that for section, for example, to highlight that I have different sections in my model. And on the right side in the control panel, I automatically get the corresponding legend to the current setting. So this is also quite nice to get a better overview of the elements that you have and objects that you have defined in your model. Yeah. So what's missing now is the load and the supports. So let's start with the nodal supports. I want to add a nodal support at the start of my beam. I want to fix it in Z and in X direction. I want to apply the same boundary conditions to my end nodes at the upper support structure, at this secondary truss structure. And since the lower member should just be a single span beam, and I don't want to get any like additional restraints in the horizontal direction of this beam, I assign a roller support to the member end, so it can move freely in X direction. If I would apply the same boundary conditions to the upper support structure, it wouldn't make a lot of sense, because here I need this horizontal restraint to actually make this stiff, the upper structure. I can imagine that when I now in the last step load my lower member, this beam member, with a vertical load of 15 kilonewton per meter. I just do that right now. Then the secondary truss member structure above it acts like some or provides some elastic supports at the thirds of the member of the single span member, and of course the stiffness of the support depends on the stiffness of the nodal supports here at the ends, also on the member stiffnesses or the truss member stiffnesses and the length and so on. And if these wouldn't be fixed in the X direction, they would just move towards each other, and I wouldn't have any additional supports provided by this upper substructure here. All right, so now everything is set for the analysis. I've defined my members, I've defined the load, I've defined the supports. So I actually can now run the simulation. I do that by asking for the results, but of course I don't have any results, so it automatically calculates. And then I can assess the results navigator and yeah, first look into my global deformations. I will switch off the loads just to make it a bit more informative or easy to see those deformations. And then I could also switch the display of these deformations. For example, I mostly like to analyze member deformations by using this option to show the sections colored, because in this way I not only get the deformation of this wireframe model, but I can directly see the intensity of the deformation by the plotted color. And moreover, I could already see if there would be some torsion in the members. I could see that by the display of this cross section. Yeah, I could directly see this, whereas in the wireframe model, I can only see the overall deformation of a certain point along the member. So that's also useful. And what I see now is that I have around 45 millimeter maximum displacement at a midsection of the single span beam down here. And of course, the upper support structure is also deforming with it. It's elongating in these truss members, because they should all of them should be under tension, and we can check that if we proceed and go to the internal forces in our system to better read the forces. I go to the wireframe model and deactivate the rendering, and now I can see that I have very large tensile forces in this above supporting structure, and a vertical load of 75, or vertical normal load, and this vertical members of 75 kilonewtons, and these would be the so to say support forces for these intermediate supports of this single span beam. The beam itself is free of axial forces, because I released the horizontal support condition at the member end, but the single span beam below has vertical shear forces and also bending moments around the strong axis. And I can see by this jump in the shear forces, I can see that part of the shear forces are transferred to the upper substructure. But the exact values I couldn't read from this exact diagram because I only get the extreme values and the values at the end of each member. However, the results are calculated on many more points as indicated in these dashed lines here. And if I want to see all values, I can go to these results options under members, and I can activate the option to show all values. And then I could also read the exact value between the left side of this intermediate node and the right side of this intermediate node. So that would be quite helpful in this case. Another way to further or to investigate the results in detail and maybe to compare different result values is to open a result diagram. Therefore, I just select a member and can use the toolbar to assess the result diagram, or I could also right-click on it and open the result diagram via the context menu. And if I do so, I get the results that I want over the whole member length. Just as you can see here, it's the member length or the actual coordinate of this member is plotted up here. So it's 60 meter 50 long, and along this length, I can now go into the design details and check every value where it not only gives me the values at the interpolation points, but it also interpolates between those points, between those result values. And I can activate as many result quantities as I want. So now I have the overall deformations, but I could and the shear forces, but I could also add the bending moments here if I want to, or the actual forces. Of course, they are 0 in this case. But that's a very neat way to compare results and also to document results. I could directly print this figure into my report, of course. Moreover, I have the possibility to average some results. I can just double click up here in this x-axis bar, and then I can create an averaging region, and it automatically calculates the average result value in this particular region, and I can interactively move it over the length of my member to get like the mean value or average value within this window here. This can also be helpful in some cases, like if you want to have average support reactions or something like this, you can use this function. This also works for multiple beams. So if I select the 3 upper truss members here and open the result diagram option, it shows me the results for all these 3 members. It indicates that above here, on top here, saying that the first section represents member number 4 from node 7 to node 5, then member number 5 from node 5 to node 6, and member number 6 finally. So that's also quite nice. All right, that's what I wanted to show you in the context of this particular example. If there are no open questions, I would proceed with the next one. Therefore, I just delete the complete structure and show what task is next on the list. So the next exercise would be to investigate trust structure, and it says it should be an ideal trust structure, or we want to model an ideal trust structure. And what does this actually means? It means that we have only axial forces in the members, and this for this to be true, we need some implicit assumptions, which are that we have perfect hinges in the connection of our trust members, that we have no imperfections of our members, so they are straight and have a perfect geometry. We don't have any eccentricity in our connection of the members, so in reality, it is often the case that the system lines of the members, for example, in this node that I highlight here between the upper chord and the diagonals or so, they are not in line. Often it is not possible. Then we only have applied loads on the nodes between members. So we don't have any intermediate loads or member or uniform member loads. Even the self weight of the members is neglected. Yeah, and these assumptions lead to a trust structure that is only loaded in internally with axial forces, and we will try to model that in the next couple minutes. The task is to then determine the support forces and internal forces, and to identify null members, so members that don't take any axial force, and also to subdivide the members in the rest of the members in the model into tension and compression members, which we can of course judge by the sign of the axial load in the members. All right. So just as a quick note, this truss is made of multiple triangles, and all the triangles have the same length of 3 meter, which means that they also have the same opening angle. So if we in the first place neglect those vertical members that divide those triangles, we can model the truss structures in cells of triangles that have the same opening angle and the same member length, and we will do that now. All right. So I want to start maybe with the first diagonal that goes from the origin to the upper right, but I know it should be have a 3 meter length, and it should also be oriented 60 degrees towards or have an inclination of 60 degrees towards the x-axis. But how can I actually do that? Because in this case, our grid doesn't really help us. And I want to show you what you could do then. One simple way to tackle this problem is we could use the member definition single general that gives us some more options to generate the beam. Of course, we first have to choose the member type and also the section as before. So we want to model the truss structure using only truss members. And in this case, we said that we want to also neglect the self weight of the members. So in this case, I choose the member type truss only N. This will only transfer axial forces and no shear forces due to self weight of the members, for example. The section will be in HEB 300 again. So with this being said, I now get this dialog to generate my member, and I can now, for our particular purpose, choose the option to create this member by the definition of length and direction. And if I click this and go to the working window, I see that to my mouse cursor there's already a member pointing in Z direction with a length of 1 meter, and I could now place it somewhere in the model. But in my case, the length of the member should be 3, and the angle in the work plane should be not 0, not 90, but 90 plus 60 degrees. So I can calculate within this input dialog, and then I can take then my member has the correct length and orientation, and I can just set as a starting node the origin and place the first diagonal of my truss. For better overview, now my first node, it was same in the example before, but I just want to show you that you have this option. It's for me hard to see the first node because it's in the origin, and there's also this global axis system by default. But I can get rid of this when I go to the display navigator, and then under the section general, I find axis systems, and I can deactivate the global coordinate system in the origin by just deactivating this this checkbox. All right. Now I want to get the other diagonal and also the upper chord. And one clever way to do this, and this also allows me to introduce another option for member generation, would be to use the rotate function. So I select my member that I now defined and choose to copy this member by rotating it. And I want to create 2 additional copies. The rotation angle now should be 60 degrees, and it should do this rotation around the y-axis. That's correct. The y-axis is pointing out of the working plane, but the origin of this rotation should be my member end, so the upper end of the first member that I have defined. And if I now click on OK, I directly get 2 additional members that have that are rotated by 60 degrees respectively. So I can also measure this just to show you. I can measure the angle between the 2 members, and you see it's rotated by exactly 60 degrees. Okay, so that would be a good starting point. Of course, now I need to add this substructure or additional diagonals and upper chords to the model to finish my truss structure. And to do this, I can use the drag and drop function. So I can just select all the members and nodes I have so far defined. Click next to the lower left node, because that would be the node that I want to connect when I copy this piece of the model, and then hold the Shift and Control button at the same time on my keyboard, and then I can with left click and going somewhere in my working window can copy this substructure, and I can also snap to the existing node or some grid points to place this substructure another time at this location. And I want to connect it with the first one, so I could just do it like this, and I would have 3 additional members very quickly. I could also just choose these 2 diagonals, copy them the same way, and that would be a big step towards the finished truss. I can also copy the upper chord the same way, just like selecting the upper 2 members Shift and Control, left clicking, dragging it to another control node, and that's how you easily finish this truss structure by just copying with the drag and drop command some substructures or pieces of the complete structure. So that's very convenient and can be done with many objects, not only with nodes or members, but also with special objects. You can use this drag and drop function. So that just leaves me with the missing vertical truss members that, so to say, divide my triangles by half. So I generate additional truss members, and I create them by selecting this upper node of my first triangle, and then I can snap to the midpoint of the first member of the lower chord. There is by default a snapping point that I can use to generate this truss member. And once I have defined the first one, I could again use drag and drop to copy them to the remaining places or locations where I need them. Or in this case, because I need to copy it 4 times, I can do it even quicker by just using the copy command, because here I can copy multiple times in one operation. So I can create 4 copies and just need to define the displacement vector. So from where to where should it move and copy the existing or selected member or structure. And I can define this displacement vector by just clicking 2 nodes. And now it will copy this member 4 times. And the distance between the copies will be 1.50 meters in X direction. I hit apply, and with one operation, I get all the vertical members that were left. Okay, then I need supports. I assign nodal supports to the end nodes of the lower chord. The left node again will be fixed in Z and X direction, and the second node will be a roller support. So I have no restraints in my model. It's statically perfectly determined this way. And then I need loads. And in the description of this task, it said we should apply 10 kilonewtons to the first and the second top node of the triangles, and a load of 20 kilonewton to the last node here in Z direction, of course. And yeah, that would be basically it. This is a bit hard to see. I can also switch to the default display properties. I can always go back to the default options if you don't find, if you know you have modified something here, but you can't find a way to turn it back, or the option that you modified, you can just set everything back to the Dlubal standard. That would also help you in most cases to get a good default setting for your display. By just clicking here in the navigator and right-clicking it, and you get the option to reset to Dlubal standard. Okay, now let's solve this model with the applied loading and try to solve the tasks that were asked. So again, we can check the global deformations, but nothing too crazy happens here. Everything that we see is expected, I would say. but the interesting part is when we look at the internal forces, and explicitly we can maybe just to make sure that we now have only axial forces in the system, we can go through them and we will find that we only have values for the internal axial forces, so for n, and these ones we want to investigate a bit more deeper. So the first task was to determine the support forces. So for evaluating those, I have to switch on the display of the support forces here in the results navigator. And one good way to check your model for sanity would be, or that would be the first one actually, to compare the sum of the support reactions with the sum of the external loads you have given onto the structure. So on the left side, we have 16.667 kilonewton. On the right side, 23.33 vertical reaction force. So they would sum up to 40 kilonewton. And this is also what we defined as an external loading on top of the upper cord. The program does this calculation for us as well. So when we take a look into the overview of the static analysis for the load case that we have solved, it sums up all the external loads and the support forces in the model, and would tell us also if there is a significant deviation between those two result quantities, because that would like indicate a poor definition or a poor convergence of our simulation. Okay, and I mean, otherwise it also makes sense that on the right side the support reaction is a bit bigger, because on that side also the external load is a bit bigger. So we wouldn't expect a symmetric result here. The second task would be to determine the null members, and that's very easy. We can see that those vertical members that we defined in the last step have no axial loading, so they are actually the null members that could be deleted without modifying or altering the results, so that they don't do anything in this configuration. And the last task would be to determine which members act in compression and which in tension. And to quickly do this, so in our program we follow the common convention that negative axial loads or axial internal forces are compressive forces, and positive axial loads or forces are tensile forces. So, and we also distinguish them in the default setting by two different colors. So the compressive forces with a negative sign have the blue color, and the tensile forces with positive sign have the red color. So that makes it very easy to see which members of the truss are loaded in compression and which are loaded in tension. And we see that the lower cord is of course loaded in tension. Also, those two diagonals pointing inwards pointing to the middle of the structure are loaded in tension, while the remaining truss members are loaded in compression, as expected. All right, so that would be it for this structure. We can adjust a few, because I see this question in the chat. We can adjust the size of some of the graphical objects by clicking on it with the right mouse button, and then we get this slider in the context menu, where we can quickly manipulate the size of this graphical object. This is true for forces or also for supports. So I can also right click on supports to make them bigger or smaller. But for the support reactions, we don't have this feature. So for them to, if you want to go a bit deeper and change the size of those arrows, or you can also change the color or the font, you can go to the displaying options, display properties, options and display properties, and you would find under results, support reactions, nodal supports, you would find settings to manipulate the size of the of these arrows. You could change the thickness of these arrows. You could change the color of the arrows or of the text. You could change the spacing between the arrows and so on, and save that. And you could also generate templates with this particular graphical settings and load them in in your next projects. So you can save and load templates for these display properties as well, so you don't have to do this for every model over and over again. All right. So then I would proceed with the next example, and that will also be a truss structure, but this time we don't want to model it by hand, but instead we want to use the blocks feature to generate such a structure. And I want to explain you what is a block, where you can find it, and what it can do for you, and how it can increase your modeling speed. All right. So for standard structures, we offer large libraries of pre-generated structures or substructures, which are called blocks. And you can assess them, for example, via this block manager function here in the toolbar, or you can find the blocks under special objects. And if you want to use those blocks, you need to work in a 3D model type. So it asks me to change the model type to 3D. This is of course okay. And now we want to select a new block from the library, or we can do that. And this would be where you end up when you go over this block manager button up here. Then this huge library of predefined structures will open, and they are sorted in various categories. So for example, we have those 2D trusses here in this category trusses 2D. And the first one in this list would actually be the one that we should import into our model. But there are, of course, several ones with varying complexity. So you could also find the truss that we just defined manually. You could find it here in the blocks manager, but the blocks manager is not limited to trusses. We have also like complete structures that you can import. We have bridges, for example, predefined that you can directly import and play around with. And the best part I want to show you about these blocks, when I select the truss type that we want to choose, you can see that I can now say where I want to insert it in my model. But this block is also completely parameterized. So Richard showed you before how you can use global parameters to parameterize dimensions of your model, but these are already parameterized. So I can, before I generate this block, I can modify, for example, the number of bays. I can use 8 instead of 6, so it would directly add 2 additional bays. I can alter the length of the base, of the outer base and the inner base. Actually, they should be 3 meters, so I directly put in the correct values. The height should be 2.5 meters, and it directly modifies the block geometry in the preview. I go back to 6 base that I want to use, and then I, besides the geometry, I also have for this particular block options to define the sections of the top, bottom, chord, diagonals, and verticals, and I will do that as well. So for the upper and lower chord, we should use an HEA profile. I just generate a new section type for that. The chord should be an HEA 300. So I just define that, and while I'm here, I can also directly define the 2 remaining section types that I need for the model. So the diagonals should have an IPE 160 section, and the posts or vertical members should be an HEA 160. All right, and it's as simple as that. This would be my 3 section types that I need, and then I can assign them. So the top chord should be HEA 300, bottom chord should be HEA 300, the diagonals should be IPE 160, and the verticals or posts should be an HEA 160 section. All right, and I can also alter the support conditions, but I will leave them in this as a standard or in the default settings for now. We don't want to calculate anything on this model. I just want to show you how to work with these blocks. So when I apply or press OK in the block dialog, this block is actually then with the configuration that I made inserted into my model. I can when I click on when I show the sections by color, I can also directly see that my sections are correctly assigned in the model. I also have the dimensions that are directly taken to the model. So that is a very easy way to generate such substructures. And I could now generate multiple of these substructures. For example, a combination of such frames and such trusses and frames to create a complete industrial hall made of steel. So that would be quite easy. These blocks are, it's still a block object, so I can still find this block that I just inserted here under the special object blocks. And I can still use the parametrization to change the objects of this block. So I can still alter the number of bays, and it will directly update it in the model. And what I also want to show you is what's behind these blocks. These blocks are generated by a script, and this is written in JavaScript. This is the programming language which is used for our in-app scripting at the moment. And the good thing is, if you want, you can modify those scripts. So they are locked by default, but you can unlock them and change them according to your preferences. And you can also generate new blocks for yourself. So if you have structures that you use every time and you want to fully parameterize them, you can just create new blocks that you can use then every time in multiple projects again and again. Of course, it needs some time to get used to this scripting environment and scripting language. But since we have so many examples in our block manager that have this JavaScript deployed here, and you can load these and copy these, you can quite easily learn how to define them and like extract pieces from different blocks to generate your own ones. So that's a huge asset, I would say, for tasks that come back over and over again. Okay. What we also see is that you might have seen it earlier, but all the objects that are generated by this block are listed here in this pink color. And that means these objects are generated objects. They are dependent on something else. And in this case, those nodes, lines, and members, they depend on this block. So whenever I change the block definition, the definition of the nodes, lines, and member will change automatically. If I want to release this dependency, I can do that by clicking on the block and say explode. And then it will delete the block, but leave all the objects and make them editable. So now now these objects would be regular objects that I could have inserted myself. But of course, now you cannot use the parameterization anymore. And one thing we should do with this model, I think, before we can leave this example, in the block, these diagonals and posts were defined as beam members with hinges at the end to release the bending around the strong axis. But one task was to replace these beams, beam type members with truss members. And these truss members, they have also, they are like beam members with internal hinges. So when we use these truss members, we don't need to explicitly define member hinges at the end to release the bending moments. And I can just select all the diagonals and the posts, switch the member type from beam to truss member, and that would be it. So in that way, we would have now the upper and lower chord as beam members, and the rest would be truss members. And that should be it for this example. As I said, we don't want to calculate anything here, just to show you what we can do with our blocks. All right. That leads us to the two more advanced topics of this online training session. And we want to now tackle a more theoretical topic, which is we want to investigate the differences between first and second order theory and how we can change between these analysis methods within our software. And in order to do so, and also because of the time is running a bit, I would say that from now on you just observe what I am doing here and listen to my explanations. If you want to after the training, model it yourself and try to achieve the results yourself, you can of course come back to the recording and do it step by step. Pause the recording if you need more time to model it or to understand it. But since it's a bit more complex topic, I would say from now on you should focus on the explanations that I'm giving on these topics. So yeah, to the background, so far everything we have modeled and calculated was calculated under the assumption that we have a linear deformation theory. So the equilibrium between internal and external forces was derived on the base of the undeformed structure. Anyways, that's not always a valid assumption. So for very slender or flexible systems, we usually have higher deformations, and these deformation of our structure, they can alter also the actions within the column within our structure. So there is a direct influence of the deformation on the loading, and this can be addressed by using a second or third order theory for the calculation. And as an example, we want to investigate a fixed column, so 10-meter column with a steel section, HEB 300 again, with a vertical load of 100 kilonewton at the column end and a horizontal load of 10 kilonewtons also at the column end. And we want to explore the differences between the first order and second order theory in the first step. All right, so let's model this column. This is again quite easy. So we model a member type beam, section HEB 300 again, and we want to have a 10-meter long column. And it was also said we should fix it completely. So at the column end, we have a fixed support. So that means not only the translations are now constrained, but also the rotations at this point. You can also see that now that since we have switched to the 3D model, we have actually 6 degrees of freedom that we need to take care of in our 3D model. So that means 3 translational degrees of freedoms, so movements in X, Y, and Z axis, and 3 rotational degrees of freedoms, so rotations around the X, Y, and Z axis. All right. Then we need the load at the column end. That could be a nodal load. And we should apply loads in 2 different directions. So we could use 2 separate definitions for the nodal load, one for the load in Z direction and one for an X direction, but we could also switch to the load type components. And here we can directly input like each force parameter and moment value at the same time. So I have just to do one definition for our loading. I want to have a vertical load of 100 kilonewton and a horizontal load in X direction of 10 kilonewton. And when I assign that to the column end, we see that this load is now displayed at the column end. Okay. Now, in the first step, let's see what the results would be using first order theory. So we just use the default settings that we for the solution that we used now along this training session and check the results. It should be quite obvious, at least when it comes to the internal forces. Of course, we have an actual load of 100 kilonewtons in compression, which does not change over the height of the member. Then we have a shear force in the strong axis of 10 kilonewtons because of this 10 kilonewton at the column end in X direction. And this also generates a bending moment along the length. At the column end or at the column base, this results in a bending moment of 100 kilonewtons, which is the sum of or the product of 10 kilonewton times 10 meter height of the column. Of course, that gives us 100 kilonewton meter. All right, so nothing too fancy. Maybe you wonder why this 100 kilonewton meter is not displayed as a support reaction. So in the default settings, only the support forces are shown. We have to activate the support reactions by clicking the respective checkboxes. And now we would also see that there is some support reaction of 100 kilonewton meter at the column end. Okay, now let's take a look to the deformations. Maybe I switch to the wireframe model so we can read the value a bit better. Not this one, but here I want to show the deformation by lines. And I see that the deformation at the column end due to this horizontal load is 63.5 millimeter. So let's see what the effect would be if we calculate the same structure and under the same load using second order theory. Therefore, I just go to the load cases and copy the first load case. This also copies all load objects in this load case. So that load case would also have this load at the column end. And now I switch the static analysis settings for this load case number 2 to static analysis setting number 2. And let's take a look. By default, when you open a new model with a basic template, we have 3 different static analysis settings predefined. The first one for first order theory calculation, the second one for second order theory, and the third one for third order theory. The difference between second order and third order is that third order theory is also applicable for large deformations and also large rotations in the model. So if you are not sure if your rotations are too large or your deformations are too large, you can always check by comparing the results according to second and third order theory. But let's see what this predefined static analysis setting looks like and what options we have here. So for a static analysis setting, we can set this analysis type. As I said, first, second, or third order theory. I can choose for the nonlinear analysis types. So second and third order theory analysis type is always a nonlinear analysis. We need to find the solution iteratively, and therefore we have different solvers that we can use. And we can also, you see on the right side, when we have the second or third order theory active, we have also a maximum number of iterations, and we can set or activate the load in different increments, in multiple increments. So we can choose to define it in multiple load steps and so on. So there are a lot of options that we can modify, but at this stage and within this online training, I would say the default options are very much okay for us. So I just take the default static analysis setting for a second order theory analysis. I apply that to my load case that I just copied. And you see when I here switch from load case 1 to load case 2, of course, load case 2 has not been solved yet, so I don't have any results for that, but the load is the same as in load case number 1. And I just calculate the results assuming second order theory. And what have we got? We see that the deformation at the column end has now increased a bit to 68.7 millimeter. And also we see directly that our reaction moment has also increased from 100 to 100 barely 107 kilonewton meter. So let's check the internal forces of our column. The actual force is still almost 100 kilonewton constantly over the height. But there is a rather large difference in the shear force over the height and also of the bending moment. So if we analyze the bending moment values, we see, and maybe we can also set the wireframe model to see that. Oh, we can't really see that on the top node, but we see that at the rigid support, we have now an increased bending moment, and that increase of the bending moment of 6.87 kilonewton meter, this directly corresponds to our vertical load of 100 kilonewton times the horizontal deflection of the column at its tip. So that would be 0.068 meter, and that would give us an additional bending moment of 6.8 kilonewton meter, and that is what we get here as a result in our static analysis according to second order theory. So we get an increase of the bending moment due to the deformation at the column end and the vertical load that is applied. I also want to show you how you can compare the results maybe a bit more easily. You could, of course, always switch between these between the load cases to show the different results, but you could also generate a new window for this model and then split the view vertically to get this result 2 times, and then you can on one window switch to load case number 1, and on the second one you analyze the results for load case number 2, and that would make it more obvious if there are any differences in the results. So you can then always activate one of the windows and adjust the result quantities to check and compare directly the results. All right, but let's switch to one window and concentrate on the next information I will give you. So as I said, in this case, we have an increase of the bending moment of around 7%, just by switching the analysis type from first order to second order theory. So that may be neglectable. I mean, it's less than 10%, but it's still, I would say, quite significant. And also the problem is that for such structures, the dependency between the load and the reaction, they are no longer proportional to each other when we take care of the deformed structure and calculate our equilibrium based on the deformed structure. So, for example, we could now, in the second load case, we can double the load. And I want to show you, let's compare the reaction we are getting now. As I said before, we had an increase of the resulting bending moment at the column base of 7%. But now if we compare the results, we have an increase of almost 15%. So we would expect 200 kilonewton meter from our horizontal load, but now we have 30 additional kilonewton meter just from the horizontal load times the deflection. So we no longer have a linear or a proportionality between the external loading and the a reaction force. So that needs to be taken or kept in mind. And we could increase that to a point where it's not even possible anymore to find a converging solution because our structure will get unstable. So which means that due to the horizontal displacement and the very large vertical force in this case, our member wouldn't be able to withstand the bending moment anymore. And this would then lead to an error when we try to calculate the system according to second order theory with such high forces. We would get a warning message that the structure is unstable and cannot be solved anymore. So we cannot find a convergent solution in this case. And this is, of course, very critical to take into consideration or to keep in mind for slender structures that can occur. And of course, you could perform a second order theory and increase your loading until it fails to find this instability load, so to say, the critical load when the structure gets unstable. But we could also use another tool to directly find this critical load that leads to an unstable structure. And that is, so to say, the introduction to the next topic that I want to go through with you. So we want to stay more or less, we want to more or less keep this statical system. We just want to remove the horizontal load for ease. So we have what remains is our 10-meter long column with a vertical load. And we want to know now investigate what is the critical load when our that makes our structure, or in this case only this column, unstable. And this particular problem is maybe already known to you. It's basically a member under a prismatic member under compression, under pure compression, with a certain boundary conditions. And this is also known in engineering as Euler case number 1. So Leonhard Euler, he dealt with such instabilities of members that are loaded in compression already in the 18th century, and he provided analytical solutions for such problem that we are now investigating 250 years later still. And we want to use the solution of Euler, or we want to compare Euler's analytical solution for this problem, which is generally accepted among the engineering scene, and we want to compare it with the results of our numerical calculation. So the next example, or the next task, is for this particular case, a clamped column under pure compressive load, to define the critical load factor of this cantilever column where it gets unstable. And for that assessment, we can use a linear stability analysis or eigenvalue analysis in RFEM 6. But to have access to that, we need to activate an additional add-on. The first add-on that we get to know in this training series, and that's the analysis add-on structure stability. When I activate this add-on in the base settings of my model, I get the option to calculate the critical load for for a specific load case or load combination that I defined. So in this case, I'm back to my loading under first order theory, and I want to calculate the critical load of my structure under this load using a linear bifurcation analysis or eigenvalue analysis, and calculate the critical compressive force that leads to instability. So I can activate this critical load calculation here in the load case or load combination tab. I have no load combination, but I could do it the same way there. And then again, as for the static analysis settings, we have two predefined stability analysis settings. And again, as before, we can see what the options for the settings are and can, of course, alter these settings. I can choose between linear eigenvalue analysis, which we want to do in this training, but there are also other options to take into consideration non-linearities of systems. So we could also use an incremental method, but that should not be subject of this of today's training session. We can also say how many eigenmodes or eigenshapes we are interested. So basically the the stability problem is used by an eigenvalue analysis, and we for each eigenvalue that we calculate with this method, we will get an eigenshape of the structure. So we will also be able to see how the structure deforms when it gets unstable. And I would say now for this very simple model, 4 eigenvalues and eigenshapes should be enough. And then there are also some different solvers that we can use for the eigenvalue determination. But again, here for such basic problem, the standard settings are very well defined, and we can go ahead and calculate the load case with this additional option to calculate the critical load. And now you see that before the structural stability analysis is done, actually a static analysis is done, because the loading in the system must be known for the eigenvalue analysis. And accordingly, we get for this load case now 2 different result options. We can choose between the results for the static analysis. That is what we have investigated so far. So we have investigated the deformations and the internal forces and so on. But we now also get the results for the stability analysis. And this is interesting because it gives us the critical load factors. These are the factors that we can multiply the external loading with in order to get our instability load, or the critical instability load that leads to an unstable system. And we also get in the and we can see them in this drop down here and also in the table. Then we also get a magnification factor. This is basically a value that can be sometimes used to multiply or to determine forces according to second order theory by just multiplying first order theory internal forces by that factor. In some codes, for example, in steel design, this is sometimes allowed, and a way to calculate second order theory bending moments without actually calculating according to second order theory. But this is not very commonly used. I just want to highlight that this magnification factor here is denoted by the alpha value, and sometimes alpha value is also mentioned as a parameter for the critical load factor. So I just want to you to not confuse this critical load factor, which is like the multiplier for the critical load determination, and this magnification factor, which at the moment is not very important to you. And in addition to these critical load factors, we also get deformation shapes for these critical for the mode shapes or for the modes where this critical load factor is corresponding to. And again, as in the static analysis, I can show the deformations on the section colored. And now I see directly that the first mode shape that I calculated corresponds to buckling of my cantilever column around the weak axis. The second mode shape has a higher critical load factor, so that mode shape would occur at a much higher vertical load, and it corresponds to buckling of this cantilever column around its strong axis. And now I calculated the critical load factor, or the first critical load factor of 4.434, and that would actually mean that I can in a second order theory analysis, I could apply a vertical load to this column of 443.4 kilonewton. So we can check that by just again copying this load case, performing a second order theory calculation, and adjusting the vertical load to 434 kilonewton. And this should still give us a stable solution. This should still work. Okay, you see it calculates and we get something. But now if we increase the load just slightly to 435 kilonewton, let's see what happens. We try to solve the problem. And we are still able to solve it. Okay, that's unexpected. Let's again analyze. Okay, I messed up the number, so it should be 444 kilonewton, which shouldn't work anymore. So that's above our critical load that we calculated with our structure stability add-on. And this should actually fail. Yeah, and it does. And now it just, again gives us the error message that the structure is becoming unstable and we cannot find a solution when we want to calculate this according to second order theory. So this is a nice finding with our stability analysis add-on. And we also get a third and a fourth eigen mode, which are higher buckling modes of the member, which are not really interesting for us because in the end, most likely the critical load factor for a structure will be the smallest one. But the critical load factor is not, and also the eigen shape are not the only interesting outputs of the analysis. We can also go to the results by member table, and there we also get effective length factors and effective length values that we can use for stability design of this steel column. So if one of you has already performed a steel design or a stability design for buckling of such columns, you have probably used the equivalent member method, and by using this equivalent member method, you need to define a critical buckling length, or for this you need as an input the critical buckling length. And actually this critical buckling length is calculated for you for a particular system by our stability analysis add-on. And what is done in the background is quite easy. So that would be the Euler or the formula that Euler determined for the calculation of the critical buckling load for those simple column systems. And when we know our critical buckling load, and that is determined by our eigenvalue analysis, we can rearrange this formula to determine our effective buckling length. And I don't know if you have or this already in mind, but for this particular Euler case number 1, L critical, or the critical buckling length, should be taken as twice the system length. And this is actually what we get from this structural stability analysis. So for buckling in the weak axis, we can analyze the effective length for buckling or for stability occurring in the weak axis here, and we get, or we could read the value of 20 meter. Same for mode shape number 2, where buckling around the strong axis is observed. We could read our effective length value of 20 meter also in this results table tab here. Yeah, so you could ask, why is this important? I mean, for this particular case, I could also look into any good textbook. It would give me the analytical formula that I have just shown you, and I could easily calculate my stability load, instability load, and the effective length factor from these tables. That is, of course, true. But with our design add-on, we can also calculate buckling length for systems where it is not so obvious. For example, we could, from this column, and this is the very last example, we could turn this into a simple moment resisting frame. I will just duplicate the columns and add a girder to it to connect these two columns. Apply 100 kilonewtons to each of the columns, and now we could do the same analysis that we have done just before, just with one column. We could even go so far and leave the length at 10 meters. It's not exactly what the example actually asked us, but anyway, we should get a solution for this, and for comparison reasons, it's probably nicer to keep it as it is. So again, we would calculate our static analysis results, and what we get here as critical load factors is quite interesting, because we see the first critical load factor didn't change at all, because for buckling around the weak axis, it didn't help the system that we have now a second column and connected them by a beam. The whole frame now would buckle around its weak axis and would have the same critical load factor as before. But let's take a look in the second mode shape. Okay, this would be asymmetric buckling, but also out of plane, so around the weak axis of each particular column. In this case, the girder would also not do much. But now, when we analyze the third mode shape, that would represent in-plane buckling of our frame that we just generated. And now, for this kind of buckling, the critical load factor increased from 12 to 38 now, because we have built a frame, and this girder, this horizontal member here on top, it actually increases the stability of the system significantly. That we can already see by analyzing the critical load factor for buckling around the strong axis of the columns. And we could also read for this, for such more complex system, it's still quite easy, or quite a simple structure, but still we could imagine that we have an industrial hall made of frames, but we could do it, analyze the effective length the same way. We could actually now, for our mode shape number 3, which is or represents this in-plane buckling, we could derive our effective length factor for the equivalent member verification check for this steel column from the Steel Design add-on, and in this case it wouldn't be 1 or 2, which we would get for Euler case number 1 or Euler case 2, but it's some value between. And this value here, the specific effective length factor for such case would depend on the dimensions of the frame, height and the bay length, but also the stiffness of the 2 or 3 members. And also on the loading. The loading could also be different for both columns, and that would also affect the effective length factor for the columns. And also for such problems, we could use the structural stability add-on to analyze not only the linear bifurcation loads or critical load factors, but also these effective length that we can then use for the design of the columns. All right, so what we talked last about is basically this last example that I just briefly show now in the PowerPoint. So we have done that a bit quicker on a more simpler model, or without such large or we minimalized the amount of changes that we needed to do to the model just to create such frame and to show you what the purpose of our calculation actually is. But anyway, it's always wise to start with a problem that you know how to solve. So to start with simple problems that you know the analytical solution for, and then increase the complexity step by step. That's generally a good approach when learning a new tool for your engineering work, such as RFEM in this case. I would definitely recommend you to start with known problems and with low complexity, and then increase the level of complexity and see if the results are still reasonable and what you expect from it. It's always good approach. All right, with this example, I would finalize today's training session. We are already a few minutes over the time. I would like to thank you for your time. Questions, I would say, all the questions that are still open, we will answer via email to you. Then for further information about our software, we have plenty of resources on our website. So check out our just newly published website on www.dlubal.com. There you can find a lot of recorded videos and webinars. You can find knowledge base articles that summarize important features and tackle engineering problems and how to approach them in RFEM. So these are very valuable. We have a lot of frequently asked questions there that can also help you learning the software. We have different tools that can help not only you as a student, but also later in engineering offices to streamline your workflows. For example, you can find load coefficients with our GeoZone tool. So that's a very nice feature. So we have very many resources and things on our website that are worth checking out. So I would definitely recommend you to. And then one last thing from our side: if you leave this webinar, you will ask to fill a survey or participate in a survey, and we would be very happy if you would do so. If you could leave us a rating and also maybe some critique if you liked it, what you liked, what you didn't like. That of course helps us to improve our training sessions, and yeah, we would be grateful if you would take 1 or 2 minutes to fill this survey. That would definitely help us just to make sure you're on the right side. I think there's also a rating system, and 5 stars are good, where 1 star is very poor performance. So just keep this in mind. It's not like school grades in Europe, but it's like a Google review where you give stars. So, with this being said, thank you again for your attention. Have a nice evening, and hopefully we see each other in the next training sessions, and you keep motivated to learn our software. All right, have fun and enjoy the evening. Bye bye.